Follow Shadow Junior Twin.
Hello everybody, hope we're all doing great. Today we're going over trees, very nice topic. Don't have to know much about them, we have to know what they are, how to add to them, and how to traverse them. And we can traverse them in 4 different ways, but they're all quite simple to understand. So let's just get straight into it. 127 days left until paper 1, loads of time. Let's go. So what actually is the definition of a tree? Well, a tree is a non-linear, hierarchical data structure. And what does this actually mean? Well, non-linear just means that it's not going in a linear manner. It has different layers to it. And hierarchical just means that the root will have different layers of the tree, where the root node, and every tree has a root node. It basically just notes the start of the tree. We're going to go over this more when we actually have a diagram in front of us. The root node is the first layer of the tree, and then that node's children's as the second layer, and those children's the third layer, and so on and so forth. However, a tree has to have an end node, which is known as the leaf node. The leaf node has no children and marks the end of the tree. So, a binary tree is a special type of tree that can only have 2 children at most. It could have less than 2 children, it could have 0 children, making it a leaf node. However, each node has to have at most 2 children. And we come across binary trees a lot in computer science, especially A-level computer science. So what are binary search trees? Well, they are a particular type of binary tree where you have a key rule that you have to follow, where the left child of a node is always less than the node's value, and the right child is greater than the node's value. And here's a binary search tree. Here's an example. And this is the type of tree that we deal with a lot if we want to easily traverse down it, and if we're dealing with data that can be sorted in this way. So, how does this work? So we have the root node to be 8, and let's say we want to add 10 to it, which we have. We know that 10 is greater than 8, so we move it right. But 3 is less than 8, so move it left. And we can actually traverse down this tree following this pattern. If we start with 8 and we want to reach, 13, we know 13 is greater than 8, 13 is greater than 10, so go right. 13 is less than 14, so go left, and we've reached it. Same way if we want to reach 7. 7 is less than 8, go left. 7 is greater than 3, go right. Greater than 6, go right. We reach 7. Would you look at that? So, however, if you're looking for the number 9, for example, we know that 9 is greater than 8, but less than 10. So we would go here, but there's nothing here, so we know 9 is not in the tree. And as we've mentioned this, we need to know how to add nodes and traverse a tree. So let's actually go into adding nodes. And we typically want to be able to add to a binary search tree because that's what we're going to get asked to mostly. Otherwise, you'll get told how the tree works and how to add to it. But if you're able to add to a BST or binary search tree, then you can add to any tree. So if you want to add 5 to a binary search tree, you would literally traverse down the tree until you reach a leaf node, which allows you to add to it. So 5 is less than 8, greater than 3, less than 6, but greater than 4. So 5 would get added right here. Let me actually do that. To the right. So it gets added right there. And if you want to add 9, as we mentioned before, 9 would go here. If you wanted to add 2, it would be over here. Nice and simple. We just have to traverse down the tree and add it to the right spot. Okay, what are the 4 tree traversals we actually need to know? Now, it might sound complicated at first, but these 3 are all very simple once you set a nice and easy rule you can follow. And the breadth first search is literally in the name of how it works. So let's get straight into them. You need to know how to execute them, so let's just go straight into them. So what is a pre-order traversal? So a pre-order traversal essentially displays a node as soon as we encounter it. So obviously we always start with the root node, so we're going to display it instantly, and then once we first encounter the node, we're going to display it. And with all of these traversals, we go left subtree, and then we go right subtree. That's how we always go. We always go left and right in all of these traversals. So that's the kind of way we're going to do it. But however, there's a very simple way to traverse these trees using the different kind of traversals. And let me go over to this slide here to show you. Here it is. So, when you want to do a pre-order traversal, put a little dot to the left of the node. If you want to do an in-order traversal, to the bottom, and a post-order traversal to the right. And let me show you why we want to do that. That's because we want to trace around the tree, and as soon as we encounter a dot, we display that node, and that will tell us the actual correct output. For example, if you want to traverse around this tree, we're going to go all the way around it from left to right, hugging the tree, and whenever we encounter a dot, we display it. It's going to work, right? We encounter F straight away, display it, then B, then A, D, C, E, all the way around, D, and G, I, H. So that it displays the correct output for a pre-order traversal. And then in order traversal, we're doing the exact same thing. We have a dot on the middle now, or the bottom. And as we go around it, when we encounter this dot, we display it. So we have A, B, C, D, E, F, G, H, I. So this is just alphabetical order, which is just luck. This isn't always going to be the case. It isn't always going to be perfectly alphabetical or perfectly ascending order in numerical sense. That just happens to be the case for this type of tree. So what this actually does, if you were to explain it, is it displays a node once its left subtree has been fully displayed, right? And if we look at the F, the root node, for example, F is displayed once all of these nodes have been visited and displayed themselves. A is displayed first because it's a leaf node. It has no like subtrees to explore, right? So let's go on to post-order traversal. Now the dot just goes on the right. Nice and simple. We're just moving the dot around the node. So if you can guess how this actually works, if we weren't to just put dots on it, what do you think's going on? Well, if we break apart this tree here, F is going to be displayed last because it's dots around here. Obviously, it's not, which is a bit annoying, but it's dots around here. And what's going to be displayed first? A is going to be displayed first. So maybe you could think that in a post-order traversal, you're going to display a node once it has been fully explored. Once both of its subtrees have been fully explored, you display it. And that's what's going on. A is displayed first because it's a leaf node, then C, then E, they're both leaf nodes, and they're on the left-hand side. D has been fully explored once C and E have been explored. And then once D's been explored, B's been fully explored because A was explored first, right? And as we move around and as we fully explored nodes, we can display them. Nice and simple, right? And there's the output. So, what about a breadth first search? So a breadth first search works exactly how it sounds. You're going to go from left to right, down each layer of the tree, and display the nodes. You're essentially, how I imagine it, you're sweeping through the tree like you're watering crops, but moving from left to right. Might be a horrible analogy, hopefully that makes sense to you. But this would be the output. And you don't actually have to split it up like this. I've only split it up like this so you can clearly see where I got the letters from different layers. Like the first layer is F, then BG, then ADI, and then CEH. But you would probably just have it all together without it being split up. Anyways, that's a breadth first search. And yeah, I went over this briefly, but a post-order traversal is the exact same as a depth first search. They have the exact same output, they do the exact same thing. A depth first search fully explores a branch before it displays its. It fully explores a node before it displays its output. Display it as output, there we go. Got a bit jumbled on my words. So we need to know how to compare a breadth first search and a depth first search. That is something that comes up. There's been a 9 marker on this comparison a couple times, and I'm going to show you the mark scheme for that 9 marker. But first, let's actually go over a couple points you can mention. So first of all, if you think about how these searches work, a breadth first search is going to be good if the node you're looking for is close to the root. If it was added a long time ago, right? Because if it's close to the root, it's going to come up quite early as you're sweeping through the tree, sweeping through different layers of the tree. Whereas a depth first search is better for more recently added nodes, for leaf nodes, right? Because it fully explores branches before it moves on to another branch. So you can also talk about their implementation. So you don't actually know how these are implemented in code. You don't need to know this. This isn't something you have to worry about. But if you do know it, you can talk about it. And you're going to see it comes up in the mark scheme, which is kind of annoying. But since depth first search uses backtracking and recursion, on average it will have a worse time complexity than a breadth first search. Because I'm pretty sure breadth first searches have a linear runtime. So here's the mark scheme for the 9 mark I talked about. So the AO1 just comes from defining the two searches, where you can just do what the traversal does and put it into words, right? Depth first goes to the left node, this becomes a new tree, it goes down left, 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 blah, 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 and then it goes back up and repeats from the start and goes right, 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 and then you take the root, right? Nice and simple. Breadth first search just sweeps through, visit all the nodes connected to it, blah, blah, blah. So the AO2 marks come from actually doing the traversals on a tree. There was a tree given in the question. I didn't go through this myself because it's 9 mark. I'm going to do all the 9 markers together at some point. But yeah, and the AL3 comes from the points I've talked about a bit. Breadth first search is more efficient when it's closer to the root, but depth is more efficient when it's further down. And then you can talk about how they are implemented and blah blah blah. The time complexities. In large trees, depth may never return a value because if a tree is super large and depth first searches explore branches fully, or subtrees fully and branches fully, then it may never reach the leaf node that was on the right hand side, if it's a really, really deep and broad tree, if that makes sense. Anyways, here's a recap. pre on the left, in on the middle, post on the right, and that's about it. Let's go to good notes and do these exam questions, which are really, really nice. I think if you know all of the questions I've gone through so far, if you know what you're talking about, they're really easy. They don't require a lot of thinking if you know your definitions. But that's not going to be the case with paper 1 and certain paper 2 questions, which is a bit frustrating. Anyways, state 4 ways that a graph data structure is different from a tree data structure. Well, a tree has root nodes, tree root nodes, and graphs don't. That's something we know from the definition of a tree. We also know that trees are hierarchical. Trees, hierarchical, graph not. Don't write this in your actual exam. Write it properly. I'm just doing it quickly for the video. And then number 3, we have trees are always connected, right? There's always going to be a node that's connected to another node via an arc or via a branch, but graphs don't have to be connected. A graph can literally look like this. These nodes do not have to be connected, but for a tree, it would have to look something like that. Okay, number 4, let's talk about trees are bidirectional. Oh, can't spell. Trees bidirectional. And then graphs can be directed, right? You see this a lot more in decision maths, where you have graphs that can only go in one direction. You also see this in computer science, where a graph could have a little arrow on it denoting that you can only go in this direction, but you can't go back up in this direction. So, let's see. Graphs have one root node. Trees have one root node. Graphs do not have a root node. Tick. Hierarchical tick. Undirected. Connect. Tick. Tick. So this cycles point is about how graphs can look like this, right? And be connected like this. This allows you to go in a cycle around it like this. But since trees are always just connected to their children, that it, you can't actually cycle round. You have to go repeat. You have to go back over the arc if you want to go like this. You can't like cycle round, if that makes sense. And you do that more in maths. Anyways, the following data is entered into a binary search tree. Draw the binary search tree with the given data in the order given. And this is important because it tells us what the root node is going to be, which is 22. We then know that 13 is less than 22, so we'll go to the left of it. 5 is less than 22 and less than 13. 36 is greater than 22. 55 is greater than 36. 14 is less than 22, but greater than 13. And then 8 is less than greater than. So that's what the tree will look like. Let's look at the mark scheme. 22, 36, 55, 13, 15, 14, 8. So nicely done. That's a very nice question. Describe how a leaf node is deleted from a binary search tree. Well, you will traverse from the root, right? Because to actually reach the leaf node to delete, we have to traverse through the tree from the root. Through BST from the root. And then once you actually reach this root, to remove it from the tree, you can set the parent nodes pointer to this leaf to be null, right? If the pointer to the leaf node is null, there's no way that you can actually reach this leaf node, and it's effectively removed from the tree. Search that traverse tree until the required node is found. Set the parent node pointer to the leaf node to null. Nice. That's going to be 2 free marks. Describe how a binary search tree can be searched for a value. So first of all, you can check if root is equivalent to the value. If so, return root. Otherwise, if less than root. This is horrible, by the way. Do not write like this. Write in full sentences. This is just for the video. Disclaimer, disclaimer. Do not write like this. If less than root, go left. If greater than root, go right. And this is me just writing down what I went through earlier when traversing binary search trees. You literally, since they're in their order, so let's say it was, let's do that a bit better. Let's say we have 2. This could be 3. This could be 1. Great, nice and simple. Which I can give 2 is equal to the value. If it isn't, if it's less than the value, we go left. If it's greater than the value, we go right. Because that's how binary search trees work. That's how they have to be created. We could write a bit more. We could say, recursively do this until you reach your target node. and so on and so forth. But we've already got 4 marks, I think. Check if the root node is equal to search value. Nice, that's going to be the first mark. Let's circle this. If so, return. Nice. If value is less than root node, take left subtree. If value is greater than root node, take right subtree. That's 4 marks easily. And you could also talk about repeating the procedure with the subtree until search value is found. That would be another 2 more bullet points you can check off. Or you can talk about how you've reached the end and then it's not in the tree. But these are really nice 4 markers, 2 markers, drawing, whatever. I don't know how many marks this was, but I reckon it would have been 3 or 4 marks. But as you can see, these are really, really nice questions for this topic. A lot of the paper 2 topics are just, if you know what you're talking about, you can get those marks. Anyways, thank you for watching, everybody.